And we are back with part 2 of June 27th's lecture. Here to learn about V and M, shear and moment diagrams by inspection. Alright, so let's begin. So, V and M by inspection, shear and moment by inspection. V and M by inspection. So, it's based on a few principles. One, vertical loads shift the shear diagram up or down. Will shift the shear diagram up or down. Up or down. And a upward load will cause a positive increase in the shear, and a downward load will cause a decrease in the shear. 2, concentrated moments cause jumps in the moment diagram. So in other words, external moments applied to the structure or to the beam cause jumps in M. In moment diagram. However, we need to be mindful of the sign here. Counterclockwise external moments will actually cause a negative jump in the moment diagram. Counterclockwise moments cause the moment diagram. So again, we need to be very careful to distinguish external and internal forces. If you apply a positive moment to the structure on the outside, inside it must resist that with a negative moment. So again, positive, a counterclockwise external moment will cause a drop, a negative increase in the moment diagram, and a clockwise external moment will cause a positive jump in the diagram. And we'll see that. Some other principles. So basically this is built upon 4 principles. 3, a free end with no concentrated force or moment. No concentrated force or moment. M is 0 and H is 0, or sorry, V is 0. And a pin or roller end. Let me label that in the red that I've used before. V equals 0, M equals 0. And on a pin or roller end, V is equal to 0. It will generally not be 0 on the end, unless you have very particular loadings. But M will be 0. So these are just our boundary conditions. Yes?
So when you're talking a free end, is that like a cantilever?
Yes, what I mean by a free end is something like this. A free end is something like this. This point here, the shear and moment have to be 0 because there's nothing there. It's just the end of the beam. Okay, and then finally, remember we will remember that these are area functions. We will remember that v of x, or let me just say, in general, v is the negative integral of w dx, and m is the integral of v dx. And both of these fundamentally are area functions. So this last step is really the core of the inspection method. We are using areas to find the shear and moment, the change in the shear and moment. Okay. So again, we're going to use areas as really our most powerful tool here. Okay. So I'm going to work through an example to illustrate this. So we're going to have a simply supported beam that has, let's see, a pin and a roller, like so. And the loading is here. Let me label the points. This is point A and this is point B. A and B. And the loadings will be AX and AY and BY. BY. We have this. And the external loading applied is a 20 Newton per meter force here. And let me draw the dimensions. The dimensions on here are going to be 4 meters, 6 meters, and 4 meters, like so. 4 meters, 6 meters, and 4 meters. And we are tasked with the following. So we are given this, and we are tasked with finding. So Guyven, our old friends Guyven and Find. Guyven and Find. No? Okay. Okay, V and M diagrams. And this whole beam is in equilibrium. Okay, so solution. Equilibrium? Some people pronounce it that way. Theoretically, I don't know. Maybe somebody does. It's important to put the right emphasis on words. Okay. So, emphasis. No? Okay. So first, the sum of moments about A. Solutions. Solution. There's only one solution. Okay, solution. So the first thing I'm going to do is the sum of moments, first thing I'm going to do is get the reactions, sorry. Step 1 is to get the reactions. And this is fairly trivial. You know how to do this by now. Hopefully. We'll find out tomorrow. Sum of moments about A equals 0. And from this, we'll just have, let's see, negative 4 meters plus 6 meters over 2 times 20 newtons per meter times 6 meters. That's the moment generated by this thing here. Plus 14 by equals 0. And by is just equal to 60 newtons upward. So I'm going through the reactions kind of quickly because we know how to do that stuff. This is easy. Y'all know this. Sum of forces in the vertical direction, upward positive. AY minus 20 newtons per meter times 6 meters plus, let's see, 60 newtons equals 0. And AY, therefore, must also be equal to 60 newtons. Another way we could have done this is we could have just said by symmetry that AY and BY both have to be equal to 60 newtons. But, oh well. And sum of forces in the x direction, we will get clearly that AX is 0. Leads us to that AX is equal to 0 newtons. So we don't need to worry about that. So we will not have any compression or tension in this member. We will only have axial force. Okay. When you get this, we'll move on and we'll find all sorts of things. You all good? Okay. Next, okay, so we have our reactions. Next, step 2 will be to draw the free body diagram. Draw a free body diagram. And this is thankfully not too bad. Draw the free body diagram. And we are going to have the forces on here are 60 newtons, are 20 newtons per meter, and a 60 Newton force. And then the dimensions are going to be 4 meters, 6 meters, and 4 meters. Like so. 4 meters, 6 meters, and 4 meters. Now, I am going to use the this to get the shear diagram, applying the principles that we saw in the first slide. Okay. So, first, let's look at this. So what is the shear diagram going to do? Well, we remember that an upward load causes an upward jump in the shear. So right at A, it's going to start out, oh, let me just label my points. This is, sorry, A and B. Okay, so right at A, initially it's at 0 before this force comes along. But what happens is, okay, an upward point force is going to cause a jump in the shear diagram. So it's immediately, it just bops right on up to positive 60. Just goes. Yes, this is the shear diagram. This is the load diagram. Yes.
So basically, we know that because the shear has to counter that upward force, but only that upward force, right?
Yes, the shear has to account for this upward force. So immediately the shear pops up. Then for the first 4 meters of the beam, there are no additional loads. There are no additional loads, so therefore the shear is simply going to be constant for the first 4 meters of the beam. Now, this downward load is going to cause the shear to decline. So I think what I'm going to do is let me put some little light, maybe little orange marks just as vertical lines that we'll see where points correspond to each other. I really like to draw these out on graph paper. That way I can actually draw them directly underneath each other. That's definitely the best way to do this. Like, these are great. This is what engineering paper is made for. Stuff's great. That stuff's great. Okay, so we need to think in terms of areas now. Remember that we saw that the shear is the area function, the integral of the load function, right? And so, and we know that a downward loading is going to cause a drop in the shear. And so how much does it drop by? Well, what is the area under the curve? So 120. So we know that doesn't tell us that it's 120 here. No, it tells us that, remember the fundamental theorem of calculus, the integral of a derivative tells you the change in the function between the 2 points. So what this tells us is the area under here is effectively negative 120. So we are going to drop by 120 units between here and here. So therefore, at this point, this has to be negative 60. And then the question is, okay, well, how do I connect them? I can make a third order curve, I could make a parabolic thing. No. How you figure this out is you look at the function above it. The integral of, this is effectively a constant value function, like y equals 5, y equals 6. Those are constant value functions. And the integral of a constant value function is a linear function. So that means from here to here, we are just going to connect the dots. Linear function. So linear function. So again, we'll have a total drop of 120 newtons between here and here because that the area of this piece here is 120. That is 6 meters times 120, or 6 meters times 20 newtons per meter, a total drop of 120 newtons. So we'll go down to negative 60 because we started at positive 60. Note, if we had 80, for example, if we had 80 here, and we had the same loading here, if this was 80, this would be down at negative 40 now. If this was at negative 40, we would actually be all the way down at negative 180. It's a drop of 120, a change of 120, a delta of negative 120 between here and here. Then, finally, in the last 4 meters of the beam, we have no more loads until the end. So it's just going to be a constant value of negative 60. And then finally, we have a vertical force and that pops us right back up to 0. So your beam, a good way to check your shear and moment is that as you go across, you should end up right back at 0. Now, we don't say the shear at, say, x equals, 14 meters is 0. We still report that as negative 60, but the curve should come back to where it started. This last reaction on the end should bring it back up to 0.
So it's 0 even though it's supported by a roller?
Well, the roller causes the beam to come back up to 0.
Okay.
If it were free, it would have stayed at negative 60.
No, if this were free, this would not have stayed at negative 60.
What would happen?
If this is a free, then our this reaction would have been much larger. And so it would actually be 0 all the way from here across. Okay. Now I'm going to use this, using the same method, same idea, to get the moment diagram. M. And the units will be Newton meters. Newton meters. Okay, so what I'm going to do is I'm going to divide this into 2 zones. So I'm going to call this maybe area 2, because this is symmetric, and this is 1 and 1. Okay, so let me find the areas. Well, area of 1, let's say area 1 is simply 60 newtons times 4 meters, or 240 newton meters.
So
That's the area of this piece here. Oh my God, that looks...
just
So
one of them.
this one and this one are going to have a total area of 240. Area 1. And then area 2, it's a triangle, 1/2 base times height, 1/2 60 times 3. And these are just the areas of these. I'll actually have to go and apply appropriate signs as need be. These are just the magnitudes. 90 newton meters. Okay, so this triangle has a magnitude of 90, 90, 240, 240. So that's really it. I know that, okay, this is a pin and a roller, so that means the moment on each of these ends must be 0. The pin, by definition, cannot resist any moment, so the moment on the ends must be 0 for this beam. So I know that between here and here, I'm going to go up by a total of 240 newton meters, because this is a positive area above the x-axis, so it's going to generate a moment, a total moment of 240 additional units. So I'm going to go up to 240. And because this is a constant value, this is going to be linear. This is going to be linear. So I'm going to put a little L there just to know it's linear. Then let me go and put another little line here. And say, okay, from this point to this point, again, this point to this point, there is going to be an increase of 90 newton meters, because that's the area of this piece. So between this point and this point, we're going to go up by an additional 90 newton meters, which means our value here must be 240 plus 90, 330. 330 newton meters. And I know that this is a linear function. What's the integral of a linear function? A parabola, yes, a parabola or a quadratic function. Like that. So I'm going to just go ahead and oh, what did I do? I'm just going to label this as a P for a parabola. And note what I did here. I started the slope at the slope of the linear equation, and I leveled it out. I said it had a slope of 0 at the peak. See, the value of the v is actually the slope of the m. Because remember, v is the derivative of m. Shear is the derivative of moment. So what we see there is that right when the shear crosses the x-axis, when the shear is 0, the moment must have a slope of 0. Or it must have a maximum or a minimum, a local maximum or a local minimum. And now now we're going to go back down. This has a magnitude, this triangle here has a magnitude of 90, but it's below the x-axis. So it will go down by 90. So we'll go down to 240. And I'll go ahead and put a P for a parabola. And finally, we'll go back down to 0. This has an area, a magnitude of 240, but it's negative. It will cause a drop of 240 Newton meters between this point and this point. And there we have it. So something to note, this entire thing is positive. So this thing, the whole thing is positive. So this is in positive bending. Or it's going to be, the beam will have a shape kind of like that. A few other notes. Yeah, oh wow. Does look like a smiley face, doesn't it? You got the eyes there. Oh, and actually, let me go ahead and label this as linear too, like on the other side. So yes, it's a beam. It's a happy beam. I didn't intend that to happen, but sometimes the world works in whimsical ways. Okay. So note. Again, just as a reminder, now I can't stop seeing it. Oh my god. M of x again is the integral of v of x, and again, the derivative of m of x dx equals v of x. V of x. Therefore, when v of x equals 0, dm dx is 0, or therefore m equals min slash max. All right, there you have it. Oh, sorry. Any questions on that?
Was this just additional information, or is this just
Those are just
explaining the relationship?
Those are just some additional information explaining the relationships that I used.
Okay.
Yes.
Sorry, when you said m equals min max, what do you mean by that?
Basically, this is just saying when shear is at with 0, the moment will be at a min or a max.
Okay.
Okay.
Yes, got it.
There's that. Okay. And I have one more example to work through, and then we'll be getting out of here a little bit early.
And the homework problem. No.
I will go ahead and post the homework solutions to, after class, though, so you have those to look at if you don't already have those solutions right now. Okay, yes.
Same format tomorrow of exam and then lecture?
Yes, the same format again tomorrow, unless you want to do the lecture first. I don't care. I mean, either way is fine for me. Okay. Or we could be really screwy and have a half hour of lecture, a 2-hour exam, and then another half hour of lecture. No? Okay.
What about a half-hour lecture, 10 minutes of exam?
Divide the exam into pieces in 10-minute intervals.
Get out.
Yes.
What if we go over the homework before the exam, and then?
I don't know if we quite have time for that, unfortunately. So yes.
I have 2 questions.
We all have questions. It's the nature of existence. It's the nature of the human condition to question. Yes. Isn't that the deep? You weren't searching for deep philosophical answers, or more like armchair philosopher answers, right? Okay. Sorry. Go ahead.
I totally lost what I was about to
Oh, I have that effect on people.
He'll come back to me.
Okay. I made him forget his question. Lovely. Oh, sorry. Didn't mean to do that. Okay. Something about the test, or something about beams, or statics.
Statics, really. I was gonna ask, from what homework to, like, from homework like 6 or 7 to now, like, what is it from?
The homework for the Houston class, the homework covers chapters 4, 6, and 7 primarily. So material from 4, 6, and 7. So you on the good side, you won't have to have any really complicated 3D vectors. So I can tell you won't have to worry much about that. So happy beams for everyone. but we will need rigid body. So basically the topics are rigid body equilibrium, trusses, frames, and shear and bending moment diagrams. That's the meat of the exam.
And you have, and is it gonna be like 6 to 8 questions?
Similar to last time, yes.
Oh, and is it the same amount of time or less time this time?
I'll give you the same amount of time.
Okay.
Okay. Okay. All right. So let me work through another example or another exemple. Exemple. Okay. So, let's see. I'm going to try to get through this one kind of quick. You got the exams to study for. So we have a cantilevered beam, points A and B, and the following forces. I am just going to go ahead and give you the reactions. I think you know how to solve for those at this point. On the end, we have a 100 Newton meter couple. So here, one of our loads is an external moment. Uh-oh. Then we have a 40 Newton point load here. And then our forces are going to be, let's say, By, let's say Bx, which will be 0, like it usually is, because we're boring people. And I'm just going to go ahead and draw this as MB, because I know it has to go in that direction. Wait, well, whatever. MB. MB. Actually, By is going to be, I'll tell you this now, 40 newtons, like this, and MB is 300 Newton meters. So I could just give you the loads and ask you to solve for it, but you know how to do that by now. Yes.
So MB is the reaction moment of the fixed support.
Yes, these are the reactions of the fixed support. Yes. So these two are the external loads, and these are the reactions of the support. 10 meters and 10 meters. And 10 meters. Now, let me draw a simplified free body diagram. So, get that, then on the next page, I'm going to draw all of my stuff below each other. So again, we just got the reactions from simple equilibria, sum of forces, etc., etc. Okay, so free body diagram. All right, the free body diagram is going to be very similar to the other one. Not that different. Going to have 100 Newton meters here. The 40 Newton here. And my vertical 40 Newton and my clockwise reaction moment of 300 Newton meters. And I will do the same kind of vertical lines I did before to connect the dots. Well, I should probably say vertical-ish. Vertical-ish lines. They have a decided slant to them, don't they? Oh well. So this is load V in newtons now. Alright, so there is no shear here. This is a free end. I only have a moment on it. I have a couple on there, but there's no moment there. sorry, there's no shear there. Stop for a moment. There's no shear there. So here, from here to the center of the beam, the shear is actually 0. The moment will not be 0, yes. Then this point force causes a 40 Newton drop. Negative 40 newtons. And then between here and here, it will be constant. And then this 40 Newton positive force will cause it to bop right back up. And that's it for the shear diagram. Yes?
Is that instantaneous, as in it's a vertical line going to 0?
Yes, this is our forces here are instantaneous. Just that's why they're called discontinuities. If they were they're not going to. We can have different types of discontinuities in equations. If they were asymptotes, they'd be going to infinity, but we typically don't deal with those in shear and moment diagrams. Typically, the discontinuities you have are vertical discontinuities. They're finite, but they're vertical. And so, yes. Okay.
So the two applied moments will not affect the shear.
Yes. Well, the one applied moment.
Oh, sorry, the one.
Yeah, the one applied moment will not affect the shear, but it will affect the the reaction moment here. Now, if I did have say like a pin support here or something, or roller support here, that would affect things a great deal because then these could generate a couple to resist or something like that. Okay.
Is there a pin or roller on this at all?
Nope, it is just a simple cantilevered beam. There is no pin or roller on here. And then finally, my M diagram. M in Newton meters here. Okay. So this 100 Newton meter force, if you remember the laws from last time, or if we remember the principles we saw last time, this, because it's clockwise, is actually going to cause an upward jump in the moment. And then it's constant across. This is 100. This was given, yes, this was given. Then, so I'm just going to label this clearly as positive. And the shape of the beam is going to be like this, in positive bending. See, you can kind of visualize this. If you have a force applied like this, if you're having trouble visualizing how this works, consider a beam like this, like a cantilevered beam, with just one loading on it. If I apply a load like this, can you see that it'll want to bend in that kind of shape? So a clockwise loading applied to the end of a cantilever beam will obviously tend to want to put it into positive bending. Again, this type of curvature is called positive bending. Negative bending is the opposite way. It's a frowny face. Okay. So then, from here to here, the dimensions here are 10 meters and 10 meters. Let me go ahead and label that. 10 meters. And this area here is going to be, well, 10 meters times negative 40 newtons, so a total area of negative 400 newton meters. And so this means this shear here is going to cause a drop of 400 between this point and this point. So this means that if we start out at 100, we'll end up down at negative 300. And because this is a constant value function, between these we must have a linear function. Close enough. Negative 300, like shown. And this is actually negative bending. So we have negative bending here. Oh, I don't like how this looks. No, 100 minus 400 is negative 300. So again, this is going to be in negative, bending like that. So it's a sad face. Yeah. So we actually have a we actually have a change. So the beam initially, so this beam, because of its complicated loading, that's the original shape, the undeformed shape. It actually starts out like that if we exaggerate it a bit, and it does something like that. Well, actually not quite like that. More like, probably more like, oh, maybe something more like, dang it. Deflected shape is going to look something like, well, it's going to be positive here, then probably switch up like that, and come back in like that. Okay. Questions on this?
So it always jumps right up to 0 at the end.
In order to get full credit, do we need to do those little boxes with the bending arrow?
No, you don't need to. You don't need to put the little boxes on there. Just make sure what you, huh?
How happy do our boxes?
Very happy. No, you don't need eyes in the boxes, no. Okay, what you do need to have is you just need to have your loads, dimensions, values, things like that. I should be able to tell what the whole system is just based off of your diagrams. So, all right, other questions? All right, if there are no questions, I will see you all for the exam tomorrow. Be sure to come prepared. Again, as a reminder, the only calculator, no graphing calculators, so do keep that in mind. Bring writing implements. You won't need anything aside from writing implements and a calculator. If you need any assistance, I'll be in my office hours later, and I'll see you all tomorrow. Have a good evening preparing, and as always, thank you.